Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Luis Cezé. Luis is graduating from the University of Illinois this year. His advisor is Professor Josep Torrellas. Luis has done a lot of work in computer architecture, including some work at IBM. He worked on the Blue Gene processor for a year, and later on he interned at IBM Research for 3 summers, I think.
Right.
And he did quite a few different works. He also worked on latency-tolerant processors. He actually worked on Kava, right, which is a better idea than run-ahead execution, I think. It works, well, which is my PhD thesis. But recently he has worked on memory disambiguation in multiprocessor systems, and he'll be talking on some of that work, and he'll be talking on some of his data-centric programming model work in this talk.
All right.
Please. Okay.
Thank you all for coming. I also like to thank Microsoft for having me here. So it's a pleasure. Actually, my first time in Seattle, so this is good. So as Anders said, my talk is on multiprocessor architecture for programmability. And since the title of the talk has multiprocessors, you're probably expecting me to start the talk with a Moore's Law plot, right? But I decided not to bore you with that. You've probably seen it enough times. So I'm just going to start saying that shared memory multiprocessors are ubiquitous. There's enough evidence because all processor manufacturers offer multi-cores. And there are 2 main reasons for that, right? They offer lower design complexity and better power efficiency. MIPS per watt is much, much better. But the problem is that sequential programs are unlikely to run much faster on these architectures. So we need to make, because of that, we need to make parallel programs ubiquitous as well, as ubiquitous as chip multiprocessors. But parallel programming is hard. Thread synchronization is especially challenging. It's prone to deadlocks, races, and live locks. Relaxed memory consistency models often confuse the programmers, as we just talking about a few minutes ago. And parallel programs are notoriously hard to debug because bugs are typically non-deterministic and very hard to reproduce. So a great challenge right now is to simplify parallel programming. And the nice thing is that with this challenge comes a lot of interdisciplinary research opportunities in improving programmability. And of course, since I'm in architecture, I believe that in this process, architecture support is key in improving programmability. Especially starting from the lower level, what we want to offer is a simple machine model. And by that I mean, my opinion right now is that it should be shared memory and a very simple intuitive consistency model such as sequential consistency, and perhaps even deterministic behavior, which we're going to talk about later in the talk. And also on top of this simple machine model, the architecture can offer primitives for better programming models, and that's especially true in terms of synchronization. So there's quite a bit of work on transactional memory now. It's being touted by the community. And I also have another synchronization model called Colorama that I'm going to give an overview later in this talk. Another thing that the architecture can offer is it can impose fewer correctness requirements on the programmer. So you could see that, for example, support for speculative parallelization offers a safety net for the programmer. The program could assume that parts of the sequential code being parallelized is parallel. And if it's not, the hardware detects a problem and re-executes it sequentially, guaranteeing correctness. So this decreases the correctness burden imposed on the programmer. And the architecture can also provide hooks for debugging. We have very large programs, especially large parallel programs, very hard to find bugs, and the architecture can play a big role in that sense. One important aspect of innovation architecture right now, in my opinion, is that all these innovations in multi-cores would not be transparent to the software. So by definition, this is the interdisciplinary nature of the problem. We have to expose these architecture features to the software. And in my thesis, I have actually made contributions in all these 4 levels of this stack that I showed here. But today, I'll focus in one main contribution, which I call bulk operation of multiprocessors. There are two papers about this, one last year and one that's coming up in ISCA later this year. And the main idea there is to provide a hardware framework for coarse-grained interactions between threads. So if you see the way, if you think about the way multiprocessors have been built so far, every single memory operation can potentially generate interaction between cores. Now, my thesis is that if you do it at a coarse grain, you have a lot of benefits, and I'm going to go through these benefits during this talk. And I'll show that using these operations, we can substantially simplify the hardware support for high-performance sequential consistency, for transactional memory, and thread-level speculation. So the key idea behind bulk operation is to summarize memory addresses accessed by a group of instructions into a signature, and then support set operation with these signatures. So the signatures describe these corresponding interactions between threads. So I want to make a group, I want to provide a framework such that a group of instructions is operated as a unit in these multiprocessors. And the goal of this research has been to provide improved programmability while keeping multiprocessor hardware simple. Remember that one of the main arguments for chip multiprocessors is that they offer lower design complexity, and we want to improve programmability while keeping this argument. We don't want to increase the complexity too much, otherwise the ideas won't be seen by industry. So let me give you an overview of what bulk operation is. The idea, as I mentioned before, is to encode a set of addresses using a hash function into a signature of fixed size. So in this hash function is based on Bloom filters. I don't know if you're familiar with Bloom filters, but the idea is hash encoding reliable errors. It's a superset encoding. So we encode a set of addresses into the signature, and the way the signatures are encoded, it's very convenient, very easy to implement in hardware, and it's very simple to perform set operations with these signatures. For example, if you want to have a set interaction, a set intersection, you just do a bitwise AND of the signatures, and the resulting signature is a superset of the intersection of the two input signatures. And using these signature operations, they form the basis of what I call the bulk framework, which is this set of hardware primitives to operate group of instructions as a unit. And on top of this framework, I've built support for sequential consistency, transactional memory, and thread-level speculation. I'm currently investigating how to support deterministic re-execution of multiprocessor using the signature operations, and also how to expose these signatures and the operations to the software to allow for very aggressive dynamic optimizations. And this bulk framework has also been picked up by other groups. So Stanford has a paper coming up in ISCA that directly builds on top of my bulk framework, and also Wisconsin they have a paper in HPCA on transactional memory that uses the signature operations from my work. So the rest of the talk goes as follows. I'm going to talk about sequential consistency and show how it can be enforced with these bulk operations. And then I'll show that this clearly, very easily extends to supporting transactional memory and thread-level speculation. And then I'll quickly outline the main idea behind deterministic execution exposing to the software. So a very important characteristic of a multiprocessor is its memory consistency model. So a memory consistency model, for those who don't know, it defines the values that a read can return in a parallel program. So it's supported by the hardware, and it has major implications on the programmability of a multiprocessor. So let me give you a very simple classic example. Imagine that you have two shared variables, flag and data, that are initially set to 0, and processor 1 sets data to 2000, then sets the flag to 1. In the meantime, processor 2 is spinning while the flag is 0, and when the flag is not 0 anymore, it reads the value of data. So the question here is, what value can this read to data return? And this is defined by the memory consistency model. So the intuitive answer for this is really, it should return 2000, right? Because P1 sets 2000 before setting the flag to 1. But depending on the consistency model, these two writes could be seen out of order by processor 2. And this read to data would return 0, which is a non-intuitive behavior of this parallel program. So I guess it's not too hard to argue that a memory consistency model affects the whole software stack. It affects how applications are written, how operating system libraries and drivers are written, how compilers generate code and what optimizations are allowed, and also eventually makes its way up to the language semantics. So I'm not saying that the language and the hardware support the same memory consistency model, but there must be an efficient mapping between the memory consistency model specified in the language and how it's mapped to the hardware. So one of the most intuitive memory consistency models, actually the most intuitive consistency model, is sequential consistency. And it's also likely what new programmers are likely to assume, programmers that are new to parallel programming. So in sequential consistency, the system behaves in a very intuitive way, as if you had a giant switch between the memory and the processors, and only one processor is allowed to access memory at a time and for a single instruction. And the switch is turned at instruction granularity, at one memory operation granularity. So having this model in mind, let's look how Lamport defined sequential consistency, actually a couple of years after I was born. And Lamport is here at Microsoft now, it's a very prominent guy. So the first aspect as defined by Lamport is per processor program order. So it defines that memory operations from individual processor maintains program order. So let me show you an example. If you have here processor 1 that issues 3 memory operations, so in the global order, these memory operations from P1 have to appear in the same order as they appear in P1's program. Now, the second aspect is single sequential order, which says that the memory operations from all processors maintain single sequential order. So, in this example, if I had a second processor that issues 3 memory operations, here P2, the resulting global order, the resulting interleaving must be observed by all processors in the system. This is the single sequential order aspect of sequential consistency. But while this is very intuitive, there are problems in enforcing it. The main problem is low performance. And the reason is this consistency model is very restrictive in terms of what memory operations are allowed to be reordered. And reordering memory operations many times help performance a lot. Or if you want to have a high performance implementation of sequential consistency, it's usually too complex. So it involves buffering a long history of memory accesses and checking this history against coherence events. So you have to, it checks against coherence events to determine, to detect if there was a consistency violation. This will be clear in a second. And these mechanisms of high-performance sequential consistency are typically tightly coupled with key processor structures, such as the load store queue, the reorder buffer, the raster file, and the cache. In these previous proposals, they rely on fine-grain or instruction-level undo when there is a consistency violation. So, for example, these are 3 important proposals on high-performance sequential consistency. They all do it at a fine grain, and they require these complex things. They're tightly coupled with key processor structures. So as a result, most current systems do not support sequential consistency. It's too complex to have high performance. But we like to change that. So our goal is to support sequential consistency with simple hardware and high performance. So let me show you what's the main idea behind that. So I call it bulk enforcement sequential consistency, or bulk SC. So let's look again at the conceptual model of sequential consistency. The processor, the switch, and the memory. And now look at this example in one possible global order. Look here that there's a fine-grained interleaving, at one instruction, very fine-grained interleaving. Now, but note that this ordering, this other possible global ordering, is also sequentially consistent. So the red instructions obey the program order in P1, the blue instructions obey the program order in P2, and the resulting global order is observed by all processors. We actually want to leverage that. So we want to group instructions into chunks and enforce sequential consistency at the granularity of these chunks, not the granularity of individual instructions anymore. So in a sense, I'm throwing away all other possible orderings and keeping only the chunk level ordering of these memory operations. So in a sense, it's as if I'm conceptually turning the switch at the granularity of chunks as opposed to the granularity of instructions. And doing that has 3 main benefits. First, it substantially reduces the hardware complexity, and I'll justify that during the rest of the talk. It enables high performance because within each chunk, memory operations can be reordered at will to achieve the best performance possible and still preserve sequential consistency. And it retains programmability because the resulting interleaving is provably sequentially consistent. So to the programmer, it appears as if the system is really sequentially consistent. But the main requirement in bulk enforcement of sequential consistency is that these chunks are executed atomically and in isolation, just like a single instruction. So let's...
You mean commit to memory?
I'm sorry?
When you say execute on that previous sentence, you mean commit to memory?
Right, yes.
Okay.
Right. So it's what is seen by other processors. Okay? So this comes exactly to this slide. So let's look in more detail what I mean by atomicity and isolation of chunk execution. So imagine that we have 2 processors here, and each one of them are executing these chunks. We don't actually stop the whole machine and allow only one processor to execute a chunk at a time, because that would restrict performance too much. So we actually allow processors to execute chunks simultaneously by using speculative execution. So let's see how we preserve atomicity. So in atomicity, the idea is that all updates in the chunk are made visible to other processor at once in an all or nothing fashion. And this is how it's, and the way this is done is all stores inside our chunk are buffered until the end, and when the chunk commits, these stores are made visible to other processors at once. So in this case, store to X and Y are made visible here, and store to W is made visible when the chunk commits. Now let's look at isolation. Isolation can be informally defined as a chunk should not see outside state changing during its execution. So here if we have the two processors again, P1 executed, stored X and Y and committed. Now P2 is also executing a chunk. And note that here I loaded X twice. This is to show a simple way to show isolation, which is loads to a variable inside a chunk should always return the same value. So reads should be repeatable. And in this case, it would not be, because processor 2 loaded X, then in the meantime processor 1 committed, and then the second load to X could see the value of, written by the other chunk, and the reads would not be necessarily repeatable. The way we enforce the illusion of isolation is that we monitor for conflicts across chunks, and if there is a conflict in this case, by conflict I mean two chunks access the same memory location. We discard one of the chunks and we execute to preserve the illusion of isolation. This is very similar to transactional memory, as I'll show later. So having that in mind, you see that the granularity of operation of a multiprocessor is these chunks, these groups of instructions. So let's look at the requirements for bulk enforcement of SC now. First requirement is we can rephrase the aspect of sequential consistency in terms of chunks now. So the per processor program order says that chunks from individual processors maintain program order. So if you have one processor, P1 here, that has two chunks, 1 and 2, the resulting global order preserves the order of P1's program of these chunks, so they appear in the same order. Now so there's a single sequential order of chunks. So chunks from all processors maintain a single sequential order. So if I had a second example to a second processor to this example, the resulting global order should be seen by all processors in the system, the resulting global order of chunks. Now, since chunks are the unit of operation, we need a very efficient way of operating with these chunks. That's where bulk, the idea of the signatures that I mentioned earlier in the talk, comes into play. So the key idea is to summarize in hardware the address is accessed by a chunk into a pair of signatures, a read signature and a write signature. A read signature describes everything that was read by a chunk, and a write signature it describes everything that was written by a chunk. And then support signature operations with very simple hardware. And operations are intersection, union, is empty, and so on. For example, union is a bitwise OR. And I'll show that much of the system operation is based on these signatures. So we operate the whole system only using signatures and signature operations. For example, when a chunk commits, it sends its write signature to other processors for disambiguation to detect if there's a conflict, and its read and write signatures are cleared. So let me show you an example with more detail. Let me show you how to support chunk atomicity and isolation in bulk using these signatures. So in this example, I have two processors, processor 1 and processor 2. I'm showing this picture the cache of the processor and the read signature and write signature for each of the processors. So P1 is executing and loads A. When it loads A, it encodes A into the read signature. So when it stores B, it encodes B into the write signature. And now note that this line here turned into red. And that's because this line in the cache now holds speculative data. And the way this is denoted is when B is when the value of B, the address of B, is encoded in the write signature, this information also tells that the corresponding line in the cache is speculative. It holds speculative data because memory has to be buffered until the end. So now if we store C, the same thing happens, and now loads D. D is encoded in the read signature. Now the chunk for P1 is completed. At the same time, processor 2 was building a chunk, it loaded B and C, and wrote to E. Now when P1 is done with a chunk and decides to commit, it sends its write signature to P2 and clears its read and write signature to proceed execution. Note that when I clear the write signature here, the lines in the cache are not speculative anymore because the information that tells what lines are speculative is also encoded in the signature. So P2 now receives the write signature from processor 1 and evaluates the following set operation. It evaluates this set expression to determine if the incoming write signature overlaps with the local read or write signature. So in this case, happens to be true, meaning that it overlaps either with the write signature W2 or the read signature R2. And if it's true, that means there is a collision. They overlap because they might have accessed the same location. So then a squash is necessary. We have to discard the work. Yes?
Why would it be bad if it overwrote the write signature but not the read signature? Seems like in that case it's just an overwrite on P2, so you can ignore it.
It's a very good question. So the reason is as follows. The granularity of addresses that I encode in the write signature are line addresses. So if they happen to overlap, we don't know how to merge.
You've got a read modify write in there, so there's really a read hiding in the write buffer.
Or, yeah, so if I encode line addresses to write signature, I have an implicit read for the rest of the line.
That's right.
Right? I have it for everything else.
So really you're intersecting it with your read set. It's just that some of your reads are recorded in your write buffer, effectively. In your
Right,
write signature.
but not because the processor explicitly read the other words, because implicit read in the yeah.
Because of the cache architecture.
Right, so now you have to merge these lines. That's a very good question. So, in fact, in the original bulk paper last year, I showed if you encode word addresses in the write signature, you actually don't need to disambiguate the write signature if you don't want to. But here I'm showing the more general case. Okay? So now what squash is necessary? It means that this processor 2 has to re-execute its chunk. And the way it does that, I'm going to show later that also using signature operations, you can discard the work. And I'll show this a little later. Now that we know how these chunks are operated with bulk, let's look at the two aspects of sequential consistency again. First is program chunk order. So in case of sequential consistency, the chunks can be arbitrarily defined from the dynamic instruction stream. For example, every 2,000 instructions. So you divide a chunk every 2,000 instructions. And a processor commits chunks in program order. This is very important. You have to preserve program order of chunks, and so you have to commit them in order. And the reason this allows high performance is because instructions inside the chunk can be arbitrarily reordered by the processor to achieve high performance. For example, if this is the original program order of the instructions, load A, load B, store C, store D. Inside the chunk, the processor can execute instructions in any order without worrying about violating the consistency model. And also, in fact, the processor can interleave execution of instructions from two in-flight chunks. For example, if a processor has a blue and red chunk, it can actually have instructions in flight inside the processor from two distinct chunks, as long as at retirement time the processor can determine to what chunk each dynamic instruction belongs to. And of course commit it in order. So you see that the processor is completely free to reorder instructions. Is this clear? Yeah? Okay, alright. So now let's see how we achieve single sequential order of chunks.
Actually, I have to admit that wasn't clear to me. Can you back up?
Okay, sure. Should I go back?
If you would. So,
yeah.
You said this statement, a processor can interleave the execution instructions from two in-flight chunks. You mean this is this memory execution here, or is this processor execution?
Memory execution. So
when I'm processor 1, when processors 2 and 3 send me these disambiguations, I can interleave the order in which I apply them to my cache?
No, sorry, so maybe I didn't make this clear. What I mean is, imagine that a processor is executing instructions. You have an aggressive out-of-order processor, for example. You could have two chunks from that one thread being executed in the processor live at the same time.
Oh, because I'm aggressively out of order. I'm so out of order that I'm actually thinking about the red chunk before I'm done with the blue chunk.
Exactly.
Okay, so that's for fine-grained parallelism within a single processor.
Right, exactly. So then the processor is free to reorder instructions completely, even across chunks, as long as at the end it commits in order. Okay? And that's because we commit them in order. Okay?
But in that case, you need more support in hardware, right? For distinguishing different chunks.
Yeah, so actually, for instance, Sun has this bit in the processor where you can flip at rename time. So you can actually determine based on... So imagine they have only two chunks. Every 2,000 instruction, when you rename the 1,000th instruction, you can flip this bit so you know at retirement time, to which one it belongs. Or you know as it's executing to what chunk it belongs, such that if it reads from memory, you can encode into the right chunk, into the right signature, I'm sorry.
So if your chunks are coarse-grained like 2,000 instructions, then there shouldn't be a...
But in the boundary there might be.
In the boundary, yeah, you will have that issue. But
right.
you will have only two different chunks present at a given time. Right,
you can allow more, but it might not make sense, because the processor might not support...
How many instructions you can look at in the processor.
Right, exactly. Depends on the effective window size. Okay? So now let's... Do you have a question? Oh, right, okay, sorry. So now let's look at the problem of single sequential order. This is an interesting problem because I'm assuming that the multiprocessor has a generic network. I'm not assuming any ordering property. I'm not assuming a bus or any ordering property inherent to the network. So in this case, I'm depicting here a point-to-point network with 3 processors. So in that case, we need an arbiter to guarantee this global total order of chunks, of chunk commits. And a very naive way of doing that is just allow a single processor to commit at a time. But this restricts performance way too much. For example, imagine that you had 3 processors with 3 chunks being executed. They all execute in parallel, but once they want to commit, only one is allowed to commit at a time. So this is another performance limitation.
So that's only a problem if commits are similar in size to the amount of time it takes to execute the instructions, right?
Right, and it can be.
Enormous chunks, that's no big deal.
That's a very good point. If you can amortize this, if you can amortize the cost of committing only one at a time, that's true. But imagine if you have a very large machine and you have to, this is a non-local communication, it might take sometimes hundreds, thousands of cycles to commit. But that's a very good point. Now, let's see how we can allow simultaneous chunk commits and still preserve global order. So here's what we had before naively, only one chunk is allowed to commit at a time, and this is what we want to do. But in order to do that, we have to obey one condition, which is the committing chunks memory operations do not overlap in any way. So if we allow these 3 chunks to commit at a time, they can't be touching the same memory positions, both for reads and writes. And I'll show that this can be efficiently enforced with chunk signatures again. So the signature describes what a chunk read and wrote, so I can use the same operations to determine when this condition is being satisfied. So let's see how we do that. Let's see how we arbitrate simultaneous chunk commits using the signatures. So here I'm showing the arbiter, and the arbiter has a pending commit list. This tells what commits in the system are pending, because the signature has to traverse the whole machine when it commits. We have 3 processors, and now these 3 processors finish their chunk execution. Now they wish to commit. So P1 happens to reach the arbiter first. So in requesting commit permission from the arbiter, it sends its write and read signature. So the arbiter checks if there's any pending commit. Since there is no pending commit, it can just immediately grant permission to P1 because nobody else is committing. Now P1 is committing, and this signature W1 stays in the pending commit list of the arbiter as long as it takes for P1 to commit. So it takes a while. I'm going to show in the next slide what exactly happens with this. So for now, just trust me that this signature stays in the arbiter for a while. So P1 is committing. Now P2 reaches the arbiter and requests commit permission and sends its write and read signature. Now there is pending commit W1. So the pending commit signature W1. So the arbiter performs again a set operation to check if one of these incoming signatures from P2 overlap with the pending signature W1. In this case, it doesn't because it checks if it's not empty. In this case, it's empty. Sorry, yeah. So it's false, not empty. So it's empty. That means that P2 is allowed to commit. So the arbiter grants commit permission to P2, and now P2 is committing at the same time. And note that signature W2 is also pending at the same time as W1. P1 and P2 are committing at the same time. Now P3 requests commit permission. The arbiter receives the write and read signature from processor 3, and it checks overlap with W1. In this case it doesn't, or W2. In this case it does overlap with W2. That means that the arbiter cannot allow P3 to commit because either one of these incoming signatures from P3 overlap with W2, and that might violate the global order. Yeah.
It's not just that you're in this one. Commit, you're also basically sending a message back to P3 to say squash, right?
Right, or it says try later. So that's...
It's going to get squashed because eventually W2 is going to arrive at P3 and P3 is going to say, oh, now I can't commit.
Oh, right. So this is another good question. Did you read the paper, by the way, or no?
I'm sorry, no.
Okay, so because you're making very good questions, so...
I thought you were saying, did you read the paper? Because then you know the answer.
No. This is a very good question. So the reason that's not true, that P3 might not be squashed, is as follows. In committing, the commit of a signature, the actual update of the memory system might not happen atomically. And it might involve, updating multiple caches of multiple processors and multiple directories. By the way, I'm assuming directory-based coherence here. So it could be the case that for parts of W2, P3 has already seen the new value, and P3 has already received W2, but it was not ready to commit yet. So P3 requests permission from the arbiter, but it happens to have already seen the update by W2 because it doesn't happen atomically in the memory system. So
I guess what I don't understand is how the signatures reflect that fact. I thought the arbiter is essentially a summary for P2 sending like when P2 commits, it sends a message saying one of the things I touched was everything in W2.
Right.
And when that arrives at P3, it doesn't matter.
But it might have already arrived. Right? So there might be a window. So actually, it happens quite frequently. The case, imagine that P2 is allowed to commit. Now, W2 is traversing the whole system, visiting the processors that might have read anything for disambiguation. That does what I showed earlier in the slide. But in this case, P3 already saw this update and happens to see the new data of P2 because it's not exactly...
Before it even started its chunk.
Before even started the commit request.
So there's communication not just between the processor and the arbiter, but between each processor and each other processor.
Right. Through the directory, yeah. This is what I'm going to show the next.
The arbiter doesn't know what processors have said among themselves.
Right.
So
it's decoupled.
The arbiter says no to P3. P3 still has to interpret and say, well, is that a hardcore no, meaning I have to do this again?
Right.
Or is it one where I permit? How does it figure that out?
So this is purely a design choice. So you could assume that that if the arbiter says P3 cannot commit, that it's very likely that P3 is going to be squashed, so you can just proactively squash P3 and that's it. But since I said P3 might already have seen W2's signature and might already have read the new data from P2 before P2 finished commit, and therefore when it receives, when it asks the arbiter for permission, it won't get squashed.
The complications are, it may have seen W2, but how do you know it may not have seen W1? That is, it doesn't know what's in the arbiter.
Right, exactly. So that's why the arbiter is saying not okay, and the processor can just wait to try the arbitration later. And in waiting, it might receive a signature and get squashed when it's waiting to be able to commit again.
Oh, I see. So is the waiting is sort of like an Ethernet backoff?
Right, exactly.
You take your chances and you
Right.
try again?
Right,
And it
exactly.
might work, it might not.
Right.
So I think I'll stop kicking this horse very soon.
No, that's fine.
Go on. But back when we were talking about the sort of the simpler version without the arbiter, where processors are telling each other to squash, the thing that my intuition for why that worked is that the communication of squashedness was
Totally ordered.
on a global, totally ordered.
Right.
And so the reason that processor 3 would know not to basically, when processor 2 said, I have written write set 2, processor 3 would say, oh, that conflicts with something I'm working on, I guess I'd better give up. There's no Lamport clock in there telling it which things were in write set 2 and so on. Now in this model, I don't understand, there's no total ordering. If we leave the arbiter out of it for commits, there's no total ordering.
Exactly. That's why we need an arbiter in an unordered network. And the arbiter is just guaranteeing that the processors are operating in different regions of memory, and therefore they don't see the activity of each other, so they can commit at the same time.
Are you telling me that processor 3 can start a chunk, in the middle of the chunk receive the W2 from P2?
Right. Read something, get the new value.
Yeah. He receives the W2. So at that point, I guess at that point at that point in the chunk execution, he knows that none of the operations before that read anything in W2, right. So he doesn't have to squash.
Right.
Then he's seen W2, so he knows it's okay to continue, having read stuff out of W2's write set, whatever processor 2 wrote. And then when he so now he knows he can commit as long as his commit is not the same time as W2, as long as W2's is done.
Right.
So the one what I'm trying to figure out is where is it recorded that P3 saw W2? I guess the fact that he continued after when he would have squashed.
Exactly. So then P3 has already seen new data from P2. Asks the arbiter, can I commit? The arbiter says no, because you might get squashed. So P3 has to wait and try again. And he might succeed.
So the fact that the W2 is out of the arbiter is enough to prove, in sort of the global sense, that P3 has safely survived W2's write.
Right, exactly. So when I'm going to show you the next slide, when this process of updating the whole machine with a new signature is done, the signature is removed from this pending list. Okay? Does that make sense to you, Ron?
Well, it just seems like there's a certain amount of magic for the processors to figure out in this case when they're told no.
No, it's
the easy case is to understand when the arbiter says no, just throw everything away. That's
Right.
an easy one.
That's an easy one, yeah.
The tricky part is the case where the arbiter said no, and you don't know necessarily what it conflicted with. It could have been W1, it could have been W2.
Right.
And you may have seen W2 and not W1.
Right.
So
in fact, there's yet a third case for that, which is you just mentioned the case. What's your name, by the way? Yeah. John. Okay. So in that case, P3 has already seen the signature from P2, and it's able to get the new data. But there's even another case, which is P3 has never seen any data, and it happens to be a cache miss that requests the data that comes from P2, but was after P2 was granted commit permission, so P3 is going to have seen the new data, so therefore it doesn't need to be squashed. So which is just it's actually a special case of what you just described. So let me show you if this, okay, I'm going to show as I said, the right signature is saying the arbiter until the commit completes. Let me show the complete commit process. If this is not clear, we can...
Just before that.
Sure.
So the processor, when it receives a not OK signal, it doesn't really need to do anything, does it?
It needs to try again.
It needs to try again at some point.
Mm-hmm.
But that try again, it needs to try again for continuation. But
right.
If it tries again, it can receive a not OK answer again, and it can try again.
Right,
also,
exactly.
Right? Until
the
OK answer, or it decides to squash.
Right. But while waiting until it gets the OK answer, you might receive the signature from W2 and get squashed.
yeah, so if it turned out that there was actually a conflict with W1, it would eventually see that before the commit completed.
Because that's what's happening.
Yeah.
Right, exactly. That's why there's no magic.
So the
Just
logic of the processor is not that complicated,
Okay.
No,
I
it's
think.
not.
If I'm
third case then,
understanding correctly.
sorry, your third case really disturbed me because you said it might be the case that P3 hasn't heard anything about W2. You got a not okay because the arbiter knows that it's going to conflict with W2, but it hasn't heard anything from W2. It
Well-
seems like in that case, if it hears anything from W2, it has to be a squash.
No, because imagine the following case. The W2 asks commit permission from the arbiter, and then it's granted permission. Then P2 automatically makes its speculative data visible to all other processors. Then after it has received the OK from the arbiter, P3 has a cache miss that happens to fetch the data from P2 that's not speculative anymore, and it's already the new value after P2 was granted commit.
That's fine, but the only at some point P3 has to receive the commit message from P2 that says, here's it's disambiguation message.
Only, yeah, right, but only if P3 has ever read or written something that...
No, that's right, but in the example, the reason it got not okay was that the arbiter observed that P3 and P2 overlapped.
Right.
So the fact that the arbiter observed that, the fact that P3 got that not okay implies that they overlapped. And if they overlapped and P3 hasn't heard from W2, that implies a squash, right?
No, not necessarily. Because of the following case. Maybe I'm making this it's really confusing.
Let's leave this for the whiteboard.
Right, okay, that's fine, but this is a good question. It's just that the only reason you might have to do the ambiguation and receive a squash is if you had read old data from P2. If you had read the new data after P2 was granted commit, you're reading the new data from P2. Okay, all right. So the complete commit process. So here I'm showing the processors, the arbiter, and the directory. By the way, here I'm assuming directory-based coherence precisely because I have an unordered network. So that means that to guarantee some coherence properties, I use a directory. Now, P1 asks commit permission from the arbiter, and the arbiter says, okay, because the pending list is empty. Now W1 is committing, and the arbiter forwards the right signature to the cache coherence directory. And the cache coherence directory receives this right signature and performs an operation called signature expansion that I haven't mentioned yet. But signature expansion is as follows. You have a signature, and you have an exact set of addresses. And the signature expansion determines from this exact set of addresses what addresses map to the signature. And in this case, the directory wants to know what directory entries might map to the incoming signature W1. And as it determines what entries the directory maps to the signature, it does two things. First, it makes P1 the owner of this data because P1 has written. So the corresponding line now has to point to P1 as the owner. And it determines what other processors might have read or written data that is encoded in W1. So it determines who needs to receive the signature for disambiguation. Okay? So the directory in this case determines that P2 and P3 happens to be shared, so it forwards W1 to P2 and P3. And now the processors perform disambiguation Okay? And as they act, when the director receives the act from all processors that receive the signature, it acts the arbiter, and the arbiter can remove W1 from the pending list. Okay? So here I show the single directory, but it's very easy to see how it can be done with multiple directories. And also, it's interesting that the whole process only uses signatures. So we changed the way these multiprocessors work now. All multiprocessors so far have been designed such that each memory operation generates an interaction. Here's just signatures, because of the coarse-grained nature of the problem. And I also show in the paper how I can build a distributed arbiter and still guarantee the global properties. If you're interested, you can look at the paper, or I can talk about it offline. Now, okay. So let's see. I told you earlier in the talk that much of the system operation is based on these signatures. But one thing that's missing now is how do we manipulate the cache in bulk using these signatures? The main operation, this is called bulk invalidation. So bulk invalidation, it gets an incoming signature, expands it, and invalidates the selected lines. So let me show you an example. Here I have a write signature W and the cache. So we perform sort of a conceptual intersection that determines what lines in the cache might map to this write signature and invalidates the resulting lines. This is called bulk invalidation. And this is used in two cases. First, when a processor receives a remote write signature, it needs to clean up all stale data from its cache. Okay, so we perform bulk invalidation with the incoming write signature. Or it can also use to discard speculative data when a squash happens. So remember that as a processor is executing and building a chunk, if it stores data, it's speculative until the chunk commits. And the information that tells what lines in the cache are speculative are encoded in the local write signature. So if you perform a bulk invalidation with your local write signature, the processor is squashing, it is cleaning up from the cache all speculative data. Is this clear? Okay. Now, the second cache manipulation in bulk is making speculative state visible. So in this case here, I'm showing the cache. There are two lines, A and B. Now, if you encode A and B in the write signature, this automatically tells that these lines in the cache are speculative. So if you want to make it visible to other processors, you just zero the write signature, and now this data is made available to other processors. They're not speculative anymore. And there's no need to update the cache. You just update the signature. So it's completely decoupled from the cache. Now, I've told you how to use the signatures for sequential consistency. But I've also showed in an earlier paper how to use these same signature operations to support transactional memory and thread level speculation. So let me just give a quick overview of what transactional memory is. Sure.
So what if you don't have enough space in your cache? Do you terminate a chunk at that point?
Yeah, you can just terminate a chunk. Because you see that it's a pure local decision of these chunk boundaries for sequential consistency. Okay. That's not true for transactional memory because this is marked in the... So we actually support overflow and describe on the paper how overflow is supported.
So that's one of the conditions for how long a chunk you get.
Right. But this is... You can usually, as a rule of thumb, you can go up to... With a 32K cache, 2-way or 4-way set associative, you can go probably 10, 15,000 instructions without overflowing your cache. Maybe even more. So in transactional memory, instead of having the chunks arbitrarily defined by the processor dynamically at will, the programmer annotates regions of the code that are supposed to be executed atomically in isolation. So in this case, the program annotated this piece of code explicitly as being a transaction, so all writes are buffered until commit, and the hardware monitors for conflicts across transactions to guarantee isolation. And if there is a conflict, it re-executes one of the transactions. So the goal of transactional memory is to provide a mechanism as a replacement for locks. And the benefit is that you don't need to worry about deadlocks or the mapping between locks and data structures and so on. Now, thread level speculation, the idea is to start with a sequential piece of code and divide this code into tasks, in this case A and B, and the hardware attempts to execute these tasks in parallel. And if they happen to have a conflict, it re-executes one of them in order to respect the original sequential order. And the main benefit is that there's no need to prove the parallelism. The original sequential order is a safety net. Look that this is different than transactions. In transactions, you have explicitly parallel code and you annotate critical sections with transactions. Here you have a sequential code and you define boundaries and the hardware has an implicit order based on the original sequential program.
Level speculation, those boundaries can be coming out of a compiler or something. It's not supposed to be programmer visible, whereas on the left, it is. Okay.
Exactly. So actually I've done work both in having compilers to break sequential programming into tests and also having the programmer breaking the... So I have one paper later I'm going to mention that provides a way of exposing these test boundaries to the programmer. So the argument here is that supporting transactional memory in TLS obviously improves programmability. And the way we can support transactional memory in TLS using this bulk framework that I presented is just, instead of arbitrarily defining the chunks from the dynamic instruction stream at will, the processor just follows the transaction boundaries or the task boundaries in TLS, and this thing just works. Okay? Except that they might be wondering that there is one piece missing. In case of TLS, we need to convey the original sequential order of transactions to the system. And this can be done in a number of ways, either through software or having the arbiter be configurable and so on.
Because you have to prevent T1 from committing before T0.
Exactly.
Okay.
Exactly. There's an implicit order. So why do I want to do things in bulk? The main advantage is that it simplifies the hardware supporting these programmability features such as sequential consistency, transactional memory, and TLS. And the main argument is that all these features are now decoupled from the core microarchitecture and caches. If you see, all previous proposals in supporting these three features relied on really overloading the microarchitecture with features and changing the way the cache behaves and so on. So, and this includes, I showed how to enforce consistency in a way that's completely decoupled from the processor. And also test ambiguation and commits is decoupled from the processor. For example, the traditional way is you have the processor structures and you have a history of memory accesses, and you have, this is just sort of a conceptual thing to show there is a very tight interaction between the logic in supporting these features and the key processor structures. Now, if you do it in bulk, the processor stays largely unmodified, and you just keep the read and write signatures just by watching the external memory stream from the processor without interacting with the inner workings. And the idea is that the processor designers can come up with the best single thread performance optimizations without worrying about multiprocessor issues, in this case sequential consistency, because everything is done outside in these chunk granularities. And we don't have a single associative structures, not even the processor and even outside the processor. Everything is based on these uniform, just bit vector signatures. They're not associative structures. There's no need to have extra bits in the cache for versioning in case of TM and TLS. It's just based on the signatures as well. Then we do all this while keeping high performance, because these signatures are superset encoding, but they don't hurt performance too much.
So it all depends on how often you have to squash.
Mm-hmm. Right.
If you end up having, say, hundreds of processors, and 10% of them are all hitting the same areas,
right,
you're going to be squashing all the time.
Yep.
Right.
But so that's exactly
style.
That's exactly the case where you have contention, though, right?
Right. Exactly the case.
I think that the reason that I'm so eager about this is that I did a software version of this just because we had a system where we needed it, and what we found is, sure, you get these cases where you have contention, but you still don't have any races, and it's much easier to go in and look at and study that contention and figure out how to tease it out, make it perform better, and in every step of the way the program stays correct, which is really a huge.
Yeah, exactly. Yeah.
One thing that's been bounced around the back of my head, maybe we're going to get to this, is these Bloom filters are supposed to be a summary of every address you've touched in the entire memory address space of the system. Mm-hmm. How big do they need to be before they have enough resolution?
So I use about 2,000 bits.
Right?
Just 2,000 bits, and it's a very regular structure. So it might sound large, but from...
It seems both large and small.
So yeah, so you're right. The size of the signature is tightly connected to the size of chunks. So 2,000 bits, right? So if you have a large chunk, you obviously you're going to have more memory accesses, and you're going to encode more stuff in a signature. So the more you encode in a signature, the more aliasing you have, the more information you lose. Because you have a fixed number of bits, the amount of information in a signature is fixed. The more you encode, the more you lose.
But even if the chunks are small, I mean, the encoding is deterministic. So it seems like the problem with such a small signature, when they look small to me, is that even with small chunks, you could have a lot of false contention, right?
Right. So, in fact, this is what intuitively you would think, but there's a very smart way of encoding the signatures such that you minimize false positives. I actually have a plot in my backup slides that shows the false positives based on the size of signatures. But as a rule of thumb, it's about, for 2,000 bits, 1 to 2% false positives. Very little.
Which is how you pick the number, I guess.
Right.
Okay.
And the signature configuration, it turns to be quite stable across benchmarks. So I have some more data. Do you have another question? No? Okay. All right.
You say,
you want me to go back?
Sorry, if you go back, you say there are no extra bits in the cache for versioning. Is that true for, what kind of nesting model are you assuming in transactional memory?
Oh, that's a good point. Another advantage of bulk is that supporting nesting you could have just one pair of read and write signature per nesting level that you support live at a time.
And you will need to have some versions for those nesting levels in the cache, right?
But everything is described by the right signature.
You still need only one signature per
Right.
nesting level.
Do you need hardware support for nesting, or do you just expose the signatures straight away to the runtime?
Oh, so this is another good question. My original paper in 06, I showed the hardware has some number of nesting levels. You support 8 or whatever you want to support. But there is ongoing work now on exposing this to software. It's fully virtualizable.
Yeah, it seems like
you can
it's like
support
DLP, right? You can tell the processor, here comes a commit, have a nice signature.
Right, exactly, yeah. So in the original paper, it's in the hardware, and you can actually, even though the hardware does not provide explicit features of virtualize, you can still find a way to virtualize it. But that's a good question. So I showed you how to use bulk for sequential consistency, transactional memory, and TLS. There's one thing that I've been working lately, which is using the same framework to replay a multiprocessor deterministically. So the idea is to have a bulk SC machine and replay a program and behaves the same way as the previous execution. And the main idea is that if you have two things, deterministic chunking of threads and have the arbiter behave in a deterministic way, if you rerun your program with very little log information, essentially only the asynchronous events, you're going to have the behavior will be reproduced. And the reason why this is better than previous approaches is that all previous approaches on deterministic replay relied on logging a tremendous amount of information that encodes the sharing between threads. Everything that was read and written and shared across threads, and they have to log this. But if you make chunking deterministic and you make the arbiter deterministic, the dependencies are implicit in the way the arbiter and the chunking behaves. So you don't have to log this information. So the result is that you have to log much less.
Does that work in the case of DMA?
What is that?
Direct memory access from hardware devices.
So I consider that is an asynchronous event.
Okay.
But it should. I mean, if the device on the other side.
You end up having to log all of those things, all of the DMA accesses.
Right. Yeah. So here, what is implicit in the ordering is accesses to shared memory. The I/O, I consider it. You have to log those and see how the device behaved.
So essentially, you treat for this purpose, you treat any device that can modify memory the same way you treat a processor.
Right.
So you'd end up having.
But if you read something
with your arbiter.
Mm-hmm. So yeah, you have right. But if you see previous work on deterministic replay relied on logging information, not only for I/O and other synchronous events, but for even shared memory, which now is implicit in the way the machine behaves. And most of the log information actually goes to plain memory, not I/O.
There are other ways, but yes.
There are, okay, right, there are.
It seems like just making chunking and arbiter behavior deterministic seems like that's the reason chunking is non-deterministic is the sort of asynchronous order that caches fill with respect to one another during speculative execution. The reason the arbiter behavior is
Right.
asynchronous is the random order that people arrive at the arbiter.
So that's a good question. By deterministic chunking, what I mean is, imagine the boundaries of the chunks are always the same. Even though you might have to re-execute, what is inside a chunk is always the same.
Because there are these things like, if you block your cache, you end up you forces your hand. You have to stop a chunk where you might not have wanted to, right?
But that should be. But the number of instructions. If you make assume that I could make chunking deterministic.
Okay.
Right.
Let's pick them small enough that we know we're not going to run out of cache.
Right.
Okay.
And you make the arbiter deterministic, you're going to have deterministic behavior. But the way you make the arbiter deterministic is that you touched a good point. It depends on the order that these events reach the arbiter. But imagine that you had a predefined order. The arbiter says, I only allow the order P1, P2, P3, P4, P1, P2, P3. Right, yeah, like a token passing.
Okay.
So therefore you have no log for shared memory at all.
What effect does that have on performance? Because the goal of doing this sort of recording should be that you have essentially so little overhead, you can be continuously logging all the time, and if anything ever happened, you can look back and say, okay, now let's see the details of how this happened.
This is a very good question, and the reason we are doing that is precisely because remember that a chunk encodes a lot. It might be very large. Therefore, you can tolerate the latency of either passing the token. So the idea is that by speculating through and executing chunks speculatively, I can tolerate the latency of having deterministic arbiter.
But do you have any numbers for what percentage slow
No,
down?
So this is still ongoing, but the number right now is we can make it between 15 and 20% slower.
Could you make it down to 1%, 5%?
So this is still ongoing. We don't know. We might. I think so, but I can prove it right now.
There are other approaches having to do with
logging synchronization only, right?
Well, no.
No?
It's basically adding hardware to effectively monitor cache miss. Because the key issue is if you can start off with a processor and you have the register state, and you have a memory model that predicts what values you'd read by whatever means, then you can deterministically replay. Now you end up, to a degree, having a model which is sort of tied up together, because if you're doing the writes to memory from that processor and then you read from it, you know what's going to be in the memory. But
if you have multiple processors
there, you have to contend with the fact that you had a cache interaction, which meant that what you got is not predictive of what you did. Mm-hmm. So the key is that you end up having to have a little bit of extra set of bits in the cache to say what parts of the cache got changed, and you have to snoop the bus.
Which is effectively logging the sharing.
Yes.
Which is what we don't want to do here.
I think what he's arguing is that you can actually escape, rather than have to log the memory bandwidth, he's only having to log the I/O bandwidth, which is...
Basically, you only have to log the ones you couldn't have predicted by straightforward prediction based on what your processor did itself. But that is, if you're running a processor, and if the reads came about because of something you wrote, you certainly don't need to write those out. Mm-hmm. But any reads that you couldn't have predicted because they came from some DMA action or some other processor changing memory, those do have to be logged.
What I think is what's interesting about what he's saying here is that he still has to log the ones from DMA accesses because they're I/O.
Right.
But unlike the approaches you're talking about, which I think I know which ones you're talking about,
he's logging the sharing essentially.
The outside of processor memory bandwidth, because by forcing the determinism, he can avoid logging it all. And so it seems like what he's saying is right now there's the other overheads are costing a lot compared to this technique, mm-hmm. But if he can figure out a way to shave those down, the nice thing is he won't be bounded by having to log that memory bandwidth.
Right, exactly.
Which could be a huge win.
Right.
Oh, yeah.
And even in the case that you just mentioned, you essentially, by what is not predictable, meaning any interprocessor interaction will not be predictable.
Yeah.
Which is what I was saying here, that you have to log the sharing. Any sharing involves an interprocessor interaction that will involve an invalidation and so on.
It's a question of where is the appropriate place to catch that. And the first observation was, if you watch what happens in the way of cache in terms of cache misses and cache line ownership, then you got that information.
Right.
Now, there may be other ways, but that's the key information, because anything you could have predicted straight away, you don't need to record.
Right. But exactly, so in this...
With the chunks.
Right.
That's right.
So all this information that you mentioned is implicit if you obey these two things. You don't have to log it at all. So the goal here is that the ultimate goal is to have a fully deterministic multiprocessor with acceptable performance. This is sort of a little ambitious, but this is sort of like long-term goal, and this is part of my future work. Yeah.
It takes care of the repro problem.
Right.
I mean, if 15% seems like a lot, but there are applications where, if you're getting 15%, but on the other hand you're getting 4 processors, there are applications where that determinism, besides debugging, where that determinism
will be valuable to any.
The question is, would you be willing to run that on your server farm?
You would if that determinism bought you something else,
right?
Like the ability to run a Paxos group or something, right? And now you have a 4-way multiproc performance, except you now have extremely high reliability because any one of those machines fails and you can keep going.
Okay.
Right.
And you can only do that with determinism. So.
Right.
No, I understand.
That's a good point. So it just means like if this 15% buys you something that in the end is profitable, yeah.
I think people are only willing to pay 1% for debuggability, but they may well be willing to pay 15%
for fully deterministic.
That's right.
Right. Yeah. So let me just tell you briefly about another ongoing work with signatures, which is the idea is expose it to software. So have a signature register file, and this signature is operations completely exposed to the software, and we can do neat things with that. So let me show you an example. Here we have the signature register file, and I have a piece of code. Imagine that I had 2 new instructions, starting coding a signature and stopping coding a signature. And here in this example I show starting coding at 0, and then you store X, load Y, and stop encode at 0. And you see that X and Y are encoded in signature at 0 here in the register file. Now, another part of the program could say encode my references into another signature S1. And the software can perform introspection and say, does S0 overlap with S1? Do they intersect? And so on. And this allows for, and also you can also check for conflict for membership with the local access stream when you're not building a signature, or even coherence events, all completely exposed to software. And this has a few uses, few interesting uses. First, for example, you can have aggressive compiler optimizations. You could have, let's say, a very aggressive common subexpression elimination, where while you're pre-computing an expression, you compute a signature of what this expression read. And before you use it, and you check dynamically if this signature is still valid. And if it is, you can just dynamically use it. And this is done just with the signatures. Now, another thing is debugging support. You could say two functions should not overlap their memory accesses. So in code, you have signatures for these functions, and later you check as an invariant they should not overlap. And if they do, this might be an indication of a bug.
So if you want to set a watch point on the memory location, this is a very cheap way to do it.
Exactly.
You just do it in code S0, read the memory location, stop S0. Now you've got a watch point set.
Exactly. And this is sort of this amorphous thing. You know, you have this set of locations encoded in the signature, and you're monitoring those. So although it's a superset, there might be issues with that, and we're investigating, but it's good enough. Right. Now, let me give you just a flavor of the evaluation. I don't want to overload and dump plots on top of you. So what I've done, I implemented this with cycle-accurate simulation using SASC. This is a simulator developed in our group. And the main results for BOCA-C is as follows. We compared it with the highest performing sequential consistency proposal called SC++ that was proposed about 10 years ago by Gnadi et al. And the result is that we could provide sequential consistency with performance comparable to release consistency, actually within 1%, which happens to be the same performance that C++ achieved, but C++ is much more complex, and it does things that are fine-grained. And in bulk, even though we had the imprecision of the signatures and everything, we're still within 1% of sequential of release consistency. Now, I also evaluated, and by the way, with BOCA-C I used commercial applications such as SpecWeb and SpecJBB, and also Splash applications, which are shared memory scientific programs. Then I also evaluated bulk for TM and TLS. I actually implemented a TM system and a TLS system using the bulk framework. And I showed that there's very little performance degradation over a typical fine-grained TM and TLS. So here's within 5%. So that means that bulk is 5% slower than if you had exactly enumerated everything that was read or written by a transaction or a task. So this is purely effect of false positives, within 5%. But the hardware is much simpler, and it seems that it's agreed that this is worth the hardware simplification. Now, I still, how much time do I have? To have 10 more minutes maybe? Or?
Yeah, we finish at 12. So.
At 12, okay, all right. So let me just give you a flavor of something that I've been working on, which is a new way of expressing synchronization. And the reason I'm explaining this, so use that this basis of my future work. So the idea is called Colorama. And we are targeting simplifying synchronization because, synchronization is hard. Lock-based synchronization, while at a coarse grain, is sort of not too hard. It offers very low performance. But you could do it at fine grain, have better performance, but it's error-prone. You have data races and deadlocks and so on. And there's also the alternative of transactional memory that's being touted to us, right? And the idea is that TM supposedly provides programmability equivalent of coarse grain locking, but the performance of fine grain locking because it's only limited by data dependencies. Now, both locks and transactions, they share a shortcoming that the programmer needs to annotate the code around every potential access to shared data. So you annotate the code to protect the data. That seemed counterintuitive to me. So the question is, if critical sections typically exist to protect access to shared data, why not annotate the data itself? And what I did is there is this proposal called Colorama, which is hardware support for data-centric synchronization. I believe that this should be, the hardware has a major role in supporting this efficiently. And there is a paper that I presented last month, a month and a half ago, on this in HPCA. So let me give you just an overview of how it works. Here on the left, I'm showing how synchronization, code-centric synchronization, which is the traditional way, is done, and on the right, the Colorama data-centric synchronization way. So suppose we have three shared variables, A, B, and C, and now every time one of these variables are accessed, the program needs to make sure that these accesses are inside a critical section. So in this case, we have lock 1 that's protecting A and B, and the reason that A and B are inside the same critical section is because they need to be manipulated atomically. They share a property that requires them to be manipulated atomically. Now C is also shared, needs to be in its own critical section. And note that here I have a different lock, L2. And the reason is because C does not need to be manipulated atomically with respect to A and B. But I'm showing locks here, but this could be simply transactions. Now, the programmer needs to make sure that not only the accesses to the data in this part of the code is inside critical sections, but also everywhere else in the code. Multiple functions, not multiple files. Now, in Colorama, here's how this could be done. The programmer declares A, B, and C. And now it determines that A and B share a property that requires them to be manipulated atomically. And I say that it colors them with the same color, in this case red. And C does not need to be manipulated atomically with A and B, so it has a different color, in this case blue. Now, the programmer writes the code without explicitly defining the critical section boundaries, because the system, based on the access stream and the colors, will be able to infer and enforce the critical sections. Okay? So let me show you an example of how this can be useful. Yeah?
So one question I have is so maybe I'm completely wrong, but in Java, for instance, you have these data structures that you can call synchronized.
You call a method synchronized, not a data structure.
You can label the whole hash table. Or, I mean, maybe it's just mapped to the left.
Java, yeah. So I get this question very frequently. Java is not purely data centric. You actually have to annotate the methods as synchronized.
You can label a whole class synchronized, and it causes all access.
All methods. So it's essentially a monitor, right?
That's right.
Yeah.
So in that case, would that be similar? It's a monitor, right? You still have to define.
It turns out the reason that that's not what people use exclusively or very often is that often monitors are a real pain to get good performance out of.
Because you don't have optimistic concurrency, right?
If you've got any public fields, then those aren't going to be protected by labeling it synchronous.
Right, exactly, yeah.
Yeah, it's programmability, it's a disaster, but
so they are not, right? You can still monitor, you can still get around these methods by accessing the public data directly. So it's not data-centric still. So let me show you an example here. In MySQL, there is this data structure that has a number of instances of this struct that has a header field and an info field. So all header fields are protected by a single global lock that's used in 29 places in the program. And the info field is protected by a per instance lock, which is used in 14 places in the program. Now, that means that if the programmer wants to protect the consistency of this shared data structure, he needs to annotate about 43 critical sections. Now, with DCS, the programmer will just color all instances of the header field, and this thing keeps falling. It just colors all instances of the header field with the same color, and each instance of the info field with a different color. And the system should be able to infer the critical sections, even if you access data directly, because it's enforced by the hardware now, together with software.
So are you going to tell us how to figure out where the critical sections start and end?
Right, yes. I'll tell you. Okay? All right. So, and the advantage is, the reasoning code-centric synchronization is non-local because the program needs to be constantly worrying about where else in the program does this critical section interfere with and make sure that everything is compatible. Now, in case of DCS, it allows you to perform local reasoning because you just focus on the data structure when you're declaring them, when you're thinking about the data. And the assumption here is that it's much easier to reason about the data than it is to reason about the code. So, and I think this should be done in the architecture. In fact, there is another work that was concurrently done with Colorama, that was in POPO 06, that they propose a software-only scheme of a data-centric synchronization for Java called atomic sets. The name of the author is Mandana Vaziri from IBM. But I think it should be done in the architecture because the main advantage is that the hardware can cheaply watch all memory references. If you do it in software only, you have to be conservative because you have lack of dynamic information. With hardware you don't, because you can watch every single memory reference. So now we need two mechanisms. A mechanism to enter a critical section and a mechanism to exit a critical section. So the way we enter a critical section is that when caller data is first touched, the hardware traps to software and the software automatically starts the critical section. So the hardware actually just provides the hooks. It doesn't actually enforce the critical section itself directly. It just traps to software and the software does whatever needs to be done to enforce that. That means you could use either locks or transactions as a synchronization substrate. So, and what the hardware needs to do is it needs to check the color of every memory access, and it needs to provide an interface to assign callers to share data. It's a form of memory tagging. The way we do that, we leverage fine-grained memory protection, but instead of just assigning protection information such as read, write, execute, we add another field called caller, which is a caller ID. Now, do you have a question?
I was just wondering how many different colors you could have.
Oh,
the more
so
colors
we actually
you have, the bigger the tag.
So we show this on the paper. There's actually a very smart encoding, and I show both from 256 to a 4 billion, which is essentially an infinite number of colors, and show that the overhead is not higher than 10% of the memory footprint, because there's a very smart encoding. We can talk about it offline. I can explain to you how it works. So now exiting a critical section. What we do is, it turns out that automatically defining the exit point just by looking at the memory, references, it's undecidable. You can't, when does it end? You don't know. So what we do is that the hardware provides flexible primitives to exit critical section based on a policy. An exit policy is a set of conditions that determines when a critical section can be safely exited. So, and the compiler inserts code that implements the defined exit policy to trigger the hardware. Okay, now, and the program must know and follow the exit policy. How? We use we use subroutine boundaries. So the return of a subroutine is determined if that subroutine has started a critical section of that caller, it ends the critical section when the subroutine returns. That's what we use on the paper, and we assess how good that policy would be based on open source parallel programs, and we see that it's actually pretty compatible with the way programs are coded today.
What's wrong? You have horrible, hard to debug race condition. You're back into the horrible world of blocks.
So it turns out that our theory is that it's easier to debug it data-centric code than code-centric code.
The reason this is I'm making all the funny faces. And
sure.
I'm imagining the exception case where you've got modular programming and you've got an outer function that calls sub-functions that do stuff, and they all need to behave. And your assumption from the programmer's point of view is, at the beginning of this function, at the end of this function, I'm going to preserve some invariant,
right.
And I don't ever actually touch the memory here. I call my minions to touch the memory, and you're going to start and end critical sections when I call my subroutines, and so you're going to get it wrong. The programmer knows, from the point of view of the code, where his invariants hold. That's why he should label it with a transaction. I mean, the idea of labeling the data seems wrong.
So actually, I think this is sort of almost a religious aspect. And I believe that the data is the way to go, because you want to protect the data and not the code.
I want to protect the data from interactions in code. I mean, you can't separate the two.
So, but then if you reason at a method level or at a function level, you have a pretty good idea that a method should be a unit of work. There's assumptions that
and what happens?
It should be atomic.
Factors that method into subunits of work.
Then it's a problem.
The programmer knows where the invariant should hold. The programmer should. The model behind transactions is that the programmer doesn't want to know how to hold the invariants, how to keep the interleavings from going bad, but the programmer should assert when the invariants hold, because that is in fact a communication from one programmer to the next, and that's the kind of thing that does belong in the code.
This is a fair criticism. So if you refactor the code, you might run into problems because of this one exit policy. That's why I say here the programmer must know and follow the exit policy. So the assumption here is that the exit policy should be intuitive enough such that you're buying something right.
The programmer says commit.
Actually, this is another policy.
Well, that's
commit
not
a specific caller.
now it's transactions.
Not necessarily, because, so imagine the case where you say, I'm done with color blue. If you haven't touched blue, that wouldn't be a critical section, wouldn't be a transaction, wouldn't be anything. Just means that if you happen to have touched blue, that would end the critical section blue, which is still halfway between code-centric and data-centric. And I'm glad you touched this point, because we actually have a second exit policy that's come in another paper that shows that this might be easier. Because now what you do is you color the data and you define what points in the code this color, this data synchronization domain is supposed to be consistent. Okay? Now, the critical sections, they might be... You label the code, yeah.
How dare you?
I know. So it breaks the purity of it. But you understand that it's not purely code-centric, because you still do not need to annotate when a critical section starts. You just say what places in the code this specific data structure, if it happens to be shared, is supposed to be consistent.
One way to judge this would be, what if the programmer forgets to put in annotations? Is the default that things will be safe but not performant?
Exactly right. So if you happen not to release a caller, for instance, so you're going to have a really overly long critical section, which is much easier to debug than a short critical section. Then if it's too short, because then you have a data race.
One of the interesting points about this is that quite often when you're thinking about data, you think about the invariants that you want to preserve. What happens when you're in the middle of a function, you're not preserving an invariant because you're making a transition. So it sounds like it might make sense to label what the invariants are in the data itself, but you've got to have a boundary which says which region of code can this be and not follow the invariants.
That's right.
Which is,
and that label is, in fact, a transaction boundary, right?
not necessarily.
Or essentially like something like that. You could, for instance, say declare the scope of a color that goes with a function, and that color is sort of allowed to be inconsistent for a while, but when you exit that scope, it should be consistent, is what you're saying.
So you're saying
basically like transaction boundaries.
Label a piece of a function as this is the section of my code where I'm making a transition in the red color. Anywhere out here,
just do it by scoping. Say, either say,
This is exactly the paper.
Like you have a declaration, say for a color, which corresponds to some sort of invariant on the data. And then when you're in that area, that means that you're doing things that are not going to violate this thing. But when you come out, you must have it fixed up.
And furthermore, whenever I'm outside here, I'm never going to touch red again, unless I come back inside one of these red sections.
Well, if you're in scope. That's what I was thinking is you mentioned a case where you have a function which wants to start making some changes, but it relies on its minions to do it. They're in the dynamic scope.
That's right.
I mean, it's an alternate way of thinking of it.
Yeah,
you're right. We do have this thing where you normally think about the invariance in terms of the relationship between the components of data. But when you're dealing with code, the whole point is that there's a point where you're violating these invariants, and it's okay because when you come out, you're going to be clean again.
Yep.
So maybe it's a scoping kind of thing.
But so in this initial paper, we actually show only the function boundary, and then we show that the same hardware mechanism could be used if you had explicit color release. In fact, we do have explicit color release in our API, and now we are evaluating exactly doing that as scope and defining what is the scope, or either there's an implicit meaning when you define the scope, or you could explicitly release colors. And if you happen to not be touching that color, fine, that thing is simply a no-op. And the way you specify the color is not saying a static color. You say the color of data structure blah. You just give it a pointer. You never manipulate colors statically. So the other paper is still not published, but if you guys want to see, I'll be happy to send you the draft. But it exactly follows the scope, and we have a model for that. And the last thing here, just quickly, is that the hardware needs structures to keep track of color ownership. And by the way, in the case of the methods, if you call multiple methods, all these color acquire and releases could be completely nested because you save and restore the state of the colors in hardware. So in conclusion, I showed you bulk, which is a versatile primitive to support to simplify the hardware support for thread interaction, and I show how to use for sequential consistency, TM and TLS, and there are other potential uses, the deterministic replay, the compiler optimizations, and debugging support. And also in terms of, and it has already spurred research in other institutions. I know there are more groups that still haven't published their work that also build on top of our bulk framework. In terms of Colorama, I believe that DCS programming simplifies thread synchronization. We are planning on doing a user study, but I'm not sure I'll be able to do it before I graduate. Probably not, but if I had the resources and the time, I'll probably try to do it. And the idea is that if this is the way to go, I think you should be supporting the hardware. It can be efficiently done in the hardware. So let me tell you quickly about my future work. So the whole idea is to continue working on simplifying parallel programming. Most of my expertise is in architecture support, and I want to think about simple, realizable architecture features that can support, that the compiler uses to support a programming model. So I want to work at these three levels, of course, with the focus on the architecture, but move these three things at the same time: the architecture support, the compiler, and the programming model. So specifically, in the medium term, I have a few ideas. In terms of data-centric synchronization, I want to clearly define color semantics, or perhaps even having different colors behave in a different way. Meaning, right now I'm assuming the colors are completely symmetric in what they mean, but could I associate a different memory behavior depending on the color? For instance, if I want to make producer-consumer extremely efficient, I could have one color that there's an implicit full empty bit. So this could be declared and associated with a specific color. And
Like a term with
what is that?
Sorry.
What is that?
Go on. Just a silly joke.
Okay, so you can tell me later. I didn't get that. So, and also thinking about compiler analysis, which is caller inference, because one of the problems with data-centric synchronization now that we just discussed is there are a lot of things that just happens dynamically. So the programmer writes code and assumes that this would work, and will just find out when the thing is already running, which might not be very good. So I'm trying to think of compiler analysis that could detect some of these errors early. And also more exit policies and using the same hardware for debugging and VM and in virtual machines. I'll be happy to talk about that later. And also there is an interesting relationship between data-centric synchronization and speculative parallelization, which I plan to investigate as well. So I also want to continue working on these bulk operations. There are other contexts. So I want to really see if I can build a fully deterministic multiprocessor using these operations, perhaps even build an FPGA prototype, not a deterministic multiprocessor, but of the software exposed signature operation. That would be interesting. And continue working on what hardware features could be used for debugging. And I actually have some ideas in using Colorama for debugging and leverage even software exposed bulk operations for debugging. Finally, during grad school, I've done other things. Besides the work on bulk and Colorama, I have a recent paper called Implicit Parallelism with Ordered Transactions, which is a set of language primitives that expose tri-level speculation to the programmer. Instead of doing it automatically, the programmer annotates the code. And it also has a tool to find parallelism in large codes. So the idea is that if I give you a very large program, let's say 1 million lines of code, and you want to parallelize it. Even though it's speculative, you're not worried about correctness, you might be completely lost if the program is too large. So we show an algorithm based on sampling that can profile an application dynamically with very little overhead and provide a report of where there might be parallelism. And if you have the source code, it automatically annotates the source code with comments for the programmer to insert these language annotations that we define on the paper. So this is the PPOP 07 paper presented last month. And I also worked on memory level parallelism. So the idea here is how do we design a memory system to support many cache misses simultaneously. And also work on checkpointed processor, which is the Kava work that Onur mentioned early in the talk. So in terms of tri-level speculation, I have also worked on compiler support, automatically defining these task boundaries, and also the architecture. And before I started grad school, I was working on the Blue Gene project at IBM, and both the memory system and the simulation aspect. I wrote a parallel simulator for the machine, full system simulator. And finally, I'm the co-maintainer of this publicly available SASC simulator that I use for my PhD. Now we actually have users from several places in the world that are using it. It's taking more of my time than I wish, but it's actually fun that people are using it for other things. That's it. So that's all I had to say. Have any other questions? Be happy to take them.
Okay. Thank you.
Thanks for the questions.